Hello everyone. In this video we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular we will continue to unpack the experimental results related to the photoelectric effect. Alright, so in the previous experiment I introduced the experimental setup for the photoelectric effect, and I introduced the idea of the stopping voltage. That is, the potential difference applied on the back end of our setup at which just barely the maximum kinetic energy of the electrons is not enough to allow them to reach the second electrode and for a photoelectric current to be detected. So let's think about that for a second. Some of these electrons do reach that maximum kinetic energy. And let us consider the relationship between the stopping voltage and that maximum kinetic energy. Well, the definition of potential difference suggests that the potential difference is the work per unit charge done on those electrons. And in this case, that just is equal to the kinetic energy, the total kinetic energy of those electrons. So the work done to slow these electrons down is exactly equal to the kinetic energy, or the maximum kinetic energy, of those electrons. And the charge in question is just the elementary charge, the charge on a single electron. And this means that the elementary charge times the stopping voltage is equal to the maximum kinetic energy of the photoelectrons. So by measuring the stopping voltage, we can measure that maximum kinetic energy of those photoelectrons, which turns out to be exceedingly useful and is the source of one of the mysteries involved with the photoelectric effect. We'll talk about that in a moment. It is important to recognize sort of what the experimental results are from this experiment. So we've got an applied potential difference here, and we are measuring our detected photocurrent. So what are the results? Well, they're summarized in this particular graph, and we'll take a look at it. So if that applied potential difference is positive, okay, that means that this electrode would be positive, and it's going to sort of pull the electrons to it, all right? So as we increase the applied potential difference in the positive direction, in this entire region, we're speeding up the photoelectrons, and we're sort of pulling them by applying that electric field in this direction here. So the electrons feel a force in this direction, and they're sort of attracted to this electrode. Notice that that increases as you catch more and more of these sort of wayward electrons, the electrons that are emitted in this direction, until eventually you reach an asymptote. That is, there is a maximum current for this applied potential difference that occurs, or that is reached, when the applied potential difference is positive enough so that it is pulling literally every electron emitted from the photosurface to the cathode itself. So the current is limited by the fact that there are only so many electrons being emitted due to the photoelectric effect, and if you're pulling them all to this electrode, then you're going to detect a maximum current, all right? So no matter how you crank up the potential difference, you're going to detect only a maximum current of as many electrons make it per unit time to this particular electrode. Notice that I could increase this maximum current, but to do that, what I need to do is release more electrons. So the way to increase the current is just to crank up the intensity of that light. That will end up releasing more electrons for reasons we'll discuss, and those electrons, those extra electrons that are emitted, will be absorbed by this electrode, and the maximum current can be increased in that particular way. Notice, though, that as I slide my applied potential difference from positive to negative, I'm going to begin slowing down the electrons in this particular region. And some of those electrons will already be going in this direction or this direction, and so they have no chance of making it to the electrode. Therefore, the photoelectric current, the photocurrent that is detected, is going to decrease all the way until Vs, which is exactly the point when the electrons with the maximum kinetic energy associated with their horizontal direction of motion no longer make it to the electrode, and there is no more photocurrent. So in this region, the electrons are all turned back before they can get to the electrode and sent in the other direction. And this is the characteristic current versus applied potential difference graph of the photoelectric effect.